Welcome to the presentation of my individual research project for the Master of Science in Advanced Computing, titled Segmentation and Interpretation of Line Charts, a Computer Vision Approach using the Faster RCNN Framework. As an introduction, according to Forbes, there are a total of 1.13 billion websites in the world, with 82% of these being inactive or receiving no maintenance. This is important because a lot of these websites may include charts with valuable data that without an API is unavailable for further processing and analysis. Moreover, individuals with accessibility needs due to visual impairments or color blindness using text-to-speech systems that cannot pass plots or images are left at the mercy of available text in the body of the website. In order to define the problem of this research project, I have taken a line chart from coinmarketcap.com, which can be seen in figure 3 on the right side here, and these type of charts are ever present in the finance world. To extract data from this chart, we need to process the important areas such as x-axis, y-axis, curve plot, currency name, and value. And to perform these operations, two of the most dominating frameworks in the computing space can be used: computer vision and deep learning. They are so popular due to their ability to generalize on unseen data if the training and optimization processes have been performed adequately. In fact, there are two existing solutions that make use of convolutional neural networks and OCR engines for text extraction. ChartOCR is a general-purpose solution developed by Microsoft that can process all types of charts. However, its accuracy depends highly on the design of the charts and the training data, and moreover, it is not offered pre-compiled to their users. On the other hand, ChartReader only processes bar plots and does not apply to the research problem. For the framework, as an evolution from the CNNs, I have used a faster RCNN, which has two-part deep learning architecture designed to specifically detect and classify objects within images thanks to the presence of region proposal networks. In order to train this model, I have created autonomous systems with Selenium that navigated and screenshotted the plot areas from different platforms, and here on the left side, a random selection of these samples can be seen. Then these samples were converted to a Pascal-VOC format necessary for the faster RCNN training. Pascal-VOC is a classification dataset type that includes the images themselves in a directory and the annotation files as XMLs containing the bounding boxes in a separate directory, being both loaded in during training. In total, there have been extracted 144,889 images of line charts divided between the four platforms, as seen here in this graphic: Binance, Crypto, CoinDesk, and CoinMarketCap. But the dataset can be further enhanced by using image augmentation, a popular technique in the deep learning world which can increase the number of samples and the generalization of the model by applying geometrical transformation to original data, such as flipping, rotating, cropping, and others. Once the dataset was ready, moving from 144,000 images to 580,000 with the augmentation, a total of 17 models were trained with different hyperparameters to reach the best performance after loading in a pre-trained model to speed up the training process. In this case, the best performance was achieved with the stochastic gradient descent optimizer with 0.001 learning rate and 0.005 weight decay over 40 epochs with a batch of 16. And once its performance is measured with intersection over union and average mean precision, as seen in figure 10, the accuracy over all areas and IOUs is between 97 and 99%, which showcases the capabilities of the faster RCNN framework to segment line charts. But a faster RCNN model is very complex, as can be seen in this video, and processing times are important. In this case, the identification of areas of interest happen within 1 second on the CPU thanks to the many optimizations to the images. Once the regions are available, OCR engines are applied with misidentification functions to extract the text. For the curve area instead, to get the lowest and highest values, a custom algorithm has been designed that fuses linear interpolation with pixel distances extracted from the plot, and within 2000 samples tested with the system in place, for the extrapolation of lowest and highest values, the lowest percentage of error was 0.001% and the average over all 2000 samples was 32%. With the system completed, there are three types of outputs that can be performed: the creation of CSV datasets making the values available for further processing, the generation of reports that can be scheduled by running the software in the cloud, such as AWS Athena or Kubernetes with Dockers, and the conversion of plots to speech through a summary based on their values. In here, Such a plot to dataset conversion can be seen in the figure on the right side, where a plot from Crypto.com was successfully converted into its original data without access to the dataset. And all of these operations are available to users through the use of a GUI that has been created with the Tinker library and ease of use in mind. And on that premise, this concludes the first section of the presentation. In this second part of the presentation, I'll be showcasing the software that has been developed specifically for this research project. After the full code is run, we are welcomed with this interface, which presents 3 buttons. By clicking Close System, the whole system will be closed. System Details will present a dialog box with information about the software, like so, and System Options will let us choose the type of processing and output that we want. Plot to Speech is my spin on a regular text-to-speech system that will convert a chart into a summary that can be heard. This is aimed specifically to users that have accessibility needs and may have visual impairments or color blindness. Dataset creation will simply create a CSV dataset that follows the tidy data principles, and repo creation will create a doc document. And so, if I go on the first button here, Plot to Speech, I can then choose between the type of input I want. A picture, a video, capturing a specific area from the desktop where the plot is, or going back to the main window. If I go and choose a picture, I can choose, for example, a sample from Crypto.com, and a processing window will be shown, and after 3 seconds I will have the output.
The current value for the currency Angola is 0.04254. This represents a drop of -43.45% in the time frame of 6 months. The currency's lowest value in the same time frame is 0.02213, meanwhile the highest value is 0.4817. These values are accurate as of 17th of August 2023.
As we can see, the output follows the data that is present in the chart, and then a dialog box informs us that the processing has been completed. The same thing can be done with the video, and I have here a sample, and it will process all the different samples in there.
The current value for the currency Angola PNCE NARD, USD, is 0.02376. This represents a drop of 5.61% in the time frame of 1 day. The currency's lowest value in the same time frame is 0.02168, meanwhile the highest value is 0.02411. These values are accurate as of 17th of August 2023.
Normally, the video will be fully processed, and in this case, if the video has been recorded at 60 frames per second for 20 seconds, then there are a lot of frames that need to be processed. In this case, by pressing the button Main Window, which will go back to the first interface, the first page, the processing stops for both the video and the desktop capture. And now I'll be showcasing the dataset creation the same way. Let's choose another picture. So let's say I want to use the Binance picture. It will process it, and then it will let me know that. And here the operation has been completed. And now you can see that I have a CSV here. And if I open it, it shows me all the different data from the plot itself that matches correctly what's in the plot. And so the last type of output that we can get is the report creation, which is the same summary as the one that is displayed in the plot to speech, but written to a text document. And if I showcase the desktop capture, it opens this window that can be moved with a left click, resized with the right click, and then the processing can be started with the middle mouse button. So I can move it on top of the plot that I'm interested in, press the scroll wheel, and then the processing will start automatically. And you can see that a document has been created here in Word. And the more I let the program run, the more frames of this chart will be processed, again, every 3 seconds. And this system can be fully ran on Linux or Windows, and it can be embedded within a Docker to run in the cloud, and so users can get scheduled outputs of specific charts that they want, and scheduled summaries as well. Again, if I press Main Window, it will go back to the main page, and you will stop the processing of the Word document. If I open it now, you can see here I have the summary of 1 frame from the plot that's here, the value of 0.02496, the increase, and everything else. And with all this said, I would like to thank you for the time dedicated, and this completes my presentation.